Yeah. Continuing with what we discussed today in the first session, um, the capacitive reactance, etc. Just one small problem, just to get a feel of how to use those equations. That's all. So just the same type of question that we discussed for inductance. Suppose I am given a purely capacitive circuit, okay, and I'm given that this capacitance is 318 microfarad. Capacitance unit will be in farads. Here I am giving a supply 230 volt 50 hertz supply. I'm asked to find out one capacitive reactance. You can write along with me. Simple problem. Capacitive reactance, RMS value of voltage and current, 3 equations for V and I. Now, having given this and so capacitance, if I want to find out capacitive reactance, I know Xc is equal to 1 by C omega. C is 318 microfarad. 318 microfarad means 10 raised to minus 6. Microfarad, 10 raised to minus 6, sir. Yes. And omega 2 pi f, 2 pi into 50. Anyway, you'll end up with 10 ohm. Again, the point that here you have to notice, this Xc is in ohms, capacitance C is in farads. Okay. What else is ours? RMS value. RMS value of current voltage is 230 itself. RMS value voltage is 230. They have already given. Current will be I is equal to V by Xc. That is 230 by Xc is 1023 ampere. And as before, I hope you know how to write the equation for V. V is equal to Vm sine omega t. Omega is 2 pi f. Vm can be found out from Vrms. Vrms is 230. So 230 into root 2 will be Vm. I is equal to, because it is a capacitive circuit, Im sine omega t plus pi by 2. That you should know. When it's a purely capacitive circuit, you should know you have to write pi by 2. Im is equal to whatever is the RMS value, 23 ampere into root. That's all. Then some other thing which is not included in your syllabus but may come is energy stored. That equation. Energy stored in an inductance is, I hope you know, it is half Li squared. And in a capacitance, it is half CV squared. Now, if they have asked you for the maximum energy stored, instead of I, which is RMS value, you have to put I max or Im. And V should be put as V max or V maximum. That's all. So that is all we have here. And then we are passing on to the next section. That is, we found that you have if it is an AC, if it's a purely DC circuit, direct current source, then you have only one element, which is resistance. But when it comes to an AC source, you have resistance, capacitance, inductance. Now we are going on to see the combination circuits. First, we'll consider series AC circuits. As you know, series circuit means the current flowing through all the elements is the same. So first we'll consider an RL series circuit. If we have understood all the concepts till now, then this is very easy. I have a resistance in series with an inductance, which will be connected to an AC source. Small v is equal to Vm sine omega t, because I am taking that as the reference. I will have a voltage drop VR here. Another voltage across the inductance will be VL. And I'll have a current I flowing through this. If capital V, now I am going to denote all these things in the phasor diagram. If I want to draw the phasor diagram, I know VR is equal to I into R. VR means the RMS value of the voltage drop. VR is IR. And I know that VL is equal to IXL, which is what we discussed now. Okay. And if I draw the phasor diagram, here there is one major difference that you should know. When I draw the phasor diagram in the series circuit, all of you should listen to whatever I'm telling you now. When I draw the phasor diagram here, I take I as, because current I is common to VR, is common to both resistance and inductance. I'll be taking I as the reference. Okay. And what will be, where will be VR lying? VR will be in phase with IR. So this is VR. What about VL? VL will be, current is lagging in an inductance. Always remember, in an inductance, current is lagging behind voltage by 90 degrees. So here, because I have drawn current as the reference, VL will be 90 degrees leading, isn't it? VL will be 90 degrees leading. What I am going to attempt is to draw the total resultant voltage. So the resultant voltage here will be like this. This is V. And that V will be leading the current through the circuit by an angle theta or phi. I'll explain that once again. Now, in this case, is a series circuit. I am taking current I as a common current because it's a series circuit. Current I is common to both resistance and the inductance connected in series. So I take I as the base or the reference vector. VR, which is the voltage drop across the resistance, will be in phase to the current flowing through it. So I have drawn VR like this. Now, in an inductance, I know current is lagging. In a pure inductance, I know current is lagging behind voltage by 90 degrees. Or I can say the same thing as voltage is leading current by 90 degrees. So what I did is, I drew this VL, the voltage across the inductance, leading by a current by an angle 90 degrees, so that I can get the resultant voltage. That is voltage which is across both R and L as V. Now this V is leading the current through the circuit by an angle phi. Okay, is this clear? Should I explain this once again? Anyone? Is this clear? Nandagopan. Nandagopan, yes, is that clear? Should I explain once again? Hello? Shivaprasad. Shivaprasad?
Yes, ma'am.
Is that clear? Should I explain that once again?
No, ma'am.
Understood. Okay. Now, which means that if there was only one resistance alone in the system, the current and voltage would have been in phase. If there was a inductance only in the system, the current would be lagging behind voltage by an angle exactly 90 degrees. But when a resistance and inductance came together, the current is lagging behind voltage not by 90 degrees, but by an angle phi. Now, we have something more to find here. Now, what is this V by analytical method? V is equal to VR plus Vj, VR or plus VR, VL. We have to add vectorially, or vectorially means actually phasor. Phasor should be added. VR is, I can write as IR plus, see, IR, this VR is IR, this VL I know is IXL. Can I add them just algebraic addition? Is that possible? No, I cannot just add mathematically like that. So, but I know that IR and IXL are shifted by an angle 90 degrees. So how will I bring that concept here? I have something known as a J operator. J operator. J, whenever I see a J coming in, I know there is a shift of 90 degrees. So IR, VR I will write as IR plus J0 plus VL I will write as 0 plus JIXL. To show that IR and IXL are not phasors along the same direction. They are shifted by 90 degrees. Or I can write this as IR plus JIXL, or I into R plus JXL. That is V is equal to I into R plus JXL, which looks same or similar to V is equal to IR. Or I can say, instead of having a resistance alone, I can have V is equal to I into Z, where Z is equal to R plus JXL is called as the impedance of the circuit. Impedance of the circuit. In any DC circuit, the opposition or whatever V by I will always be equal to R. In an AC circuit, V by I will always be equal to Z, where in this particular case, Z is equal to R plus JXL. I hope you understood the concept of J. J means a shift of 90 degrees. In this case, if you closely watch, you will understand that I have VR in this direction. I cannot add VR and VL just like that. 5 plus 6, you cannot add like that. I can only add them vectorially, or VR plus, to show a 90 degrees shift to XL. I have to show VL like this. XL, I have to introduce a J operator. Now J shows a 90 degree shift. J is equivalent to root of minus 1 actually. We will come to that later on. You needn't think about that now. Now all these conversions, all may I erase this? Or maybe I can take a new one. This is a very important concept. V is equal to IZ in any AC circuit. That is equal to I into Z in our case, because it is an RL circuit, R plus JXL. Now, what is the magnitude of Z? Magnitude of Z will be square root of R square plus XL square. As you know, if R and XL, I can write as 5 plus J3 or 4 plus J3. I know that magnitude is 5. Angle can also be found out. Angle can also be found out. Tan inverse of, or what I hope. Have you learned about rectangular and polar form of representation of vectors? Varsha?
I don't remember, ma'am. I'm not sure.
See, if you have 5, see, suppose you have a vector I'm taking xy coordinates. Suppose I have a vector like this. Okay, having say 3 and having 4 as the x and y coordinates respectively. This vector can be represented as x plus jy. So 3 plus j4 എന്ന് പറയാം. That is called as a rectangular form of representation. Okay. The same vector can be represented in the polar form also. Polar form means square root of 3 plus j4 magnitude. This magnitude will be 5, right? Square root of 3 squared plus 4 squared. And this angle, theta or phi, whatever be the angle. 5 angle 5. So this is called as polar form. Whatever it is, now what I have end up with in this particular case is to represent this waveform, this phasor. This phasor. How to represent this phasor? This phasor can be represented as VR squared plus VL squared square root, or I can represent it as I into Z, or I can represent this magnitude with this angle. So what I want all of you to do is this kind of conversion, and all these things are available in your calculator, where they have given you instructions. It depends for it differs from calculator to calculator. That is why I'm not giving you the steps. Polar form and rectangular form. Okay, so here magnitude is said is r squared plus this thing, and phi, the angle, this is magnitude. Okay, an angle phi will be given by tan inverse of XL by R. Hope you have understood. If there is any doubts, you have to ask me. Now this phi I am giving, it's a very important concept, because this is the angle phi by which the current is lagging behind the voltage in the RL network. Okay, we'll come to this later on also when you do a problem. I hope then it will be much more easier for you. And also phasor. So if I draw the waveform, this is omega t or theta. This is say voltage. I'm drawing this voltage. Okay. And if I draw the current. So what did I understand from this? Here, I saw that voltage, the resultant voltage V, is leading current I by an angle phi. Or I can even put it like this: their current through the circuit is lagging behind the voltage, the resultant voltage, overall voltage, by an angle phi. So I can write the equation as, in this case, the equation will be, if I write in the same form, V is equal to Vm sine omega t. I is equal to Im sine omega t minus phi, not pi by 2. V is equal to Vm sine omega t. I is equal to Im sine omega t minus phi. How did I get that? I had this current, I drew this current I like this, and the V, the resultant voltage V, I got it like this, and there was an angle phi. Okay. Now, which means when I draw the waveform of current I should be drawing in it such a way that it lags. So this is 0, pi, 2 pi, in such a way that I should be, the current should be lagging by an angle, if this is phi, this angle, and not pi by 2, which means I'll get a current waveform like this, which is lagging. Okay, which is lagging. Will be like this. Sorry, I've drawn it little bit, because I'm not drawing to scale, this happens. When you draw, make sure that it is to at least to some scale so that it won't go wrong. This is 5. This point, it should then cross this point. It should then cross this point somewhere here. So I should draw current waveform like this. Okay, this is my current. This is my voltage. And the power curve will be slightly different from whatever we have drawn till now. From 0 to 5, from 0 to 5, voltage is positive, current is negative. So you will have and the magnitude also will be small. This is the power. From this to pi, we'll be drawing up to pi, okay? Up to pi, voltage is positive, current is also positive. So you will get a waveform like this. This is power curve. From here to here, okay, from here to here, from pi to the next crossing of the current, pi plus 5, this will be pi, one more 5. So this current is positive, but voltage is negative. Again, you will have a small power here, small negative power. This is positive power, this is negative power. And then from here to 2 pi, this is 2 pi, okay, this is 2 pi. You will have again a positive because both are negative and so on. Okay. Here we will have a small negative also. This is how it proceeds, which means instead of having equal positive and negative power curves, here you have positive power curve more and negative also is there. Now, this happens because the positive power is consumed both in, it is not consumed, you have a positive power being consumed by a resistance and you have a positive power utilized by inductance to make its magnetic field, and then in the other half it gives away that to the source. That is the small power that you have see at the bottom. Okay, so you have again a pulsating power, but naturally if you think about it, you will understand that when you find out the equation for power, there should be two components. One component should be the component representing the power consumed by the resistance, and the other component should be the fluctuating power, which is the power given to the magnetic field and taken away from the magnetic field in the inductance. So let us derive that equation and then maybe we'll take a breather there. Okay, I hope this is clear. You are not responding, that is why I am having a lot of only if you respond, or maybe if you're finding out very boring, then I'll just stop it there. That's all. But no one is saying anything. That's why I'm continuing. So instantaneous power. Instantaneous power P is equal to VI. V is equal to Vm sine omega t. I will be Im sine omega t minus phi, some angle phi, not pi by 2. So this I can write as Vm Im by 2 into 2 sine omega t minus phi. Your trigonometrical this thing. Okay. By that you can write Vm Im by 2. This by conversion I can write as cos phi minus cos 2 omega t minus phi. Correct me if I am wrong. 2 sine A sine B can be written like this. Cos A minus B minus cos A plus B. That is what I have written. Okay. This means that I have two components, 1 by 2 Vm Im cos phi minus 1 by 2 Vm Im cos 2 omega t minus phi. I have two components here. One component is this, another component is this. Tell me which is the constant value. I told you because you have a resistance and an inductance in the circuit. Naturally, when I talk about the power, power should be consumed by the resistance and some amount of power will be taken in by the magnetic field given back to the source. So fluctuating or a energy which is fluctuating to and fro should be there. So that is represented by these two components. Tell me which is the constant component.
Cos phi.
Cos phi. Phi is a constant value. Very good. Phi is a constant value because phi is the angle by which the voltage and current is differing. That angle is determined by Z. Okay, because that is why I said from Z you get tan inverse of XL by R on I phi, which means cos phi is a constant. This is a constant term and this is a fluctuating term. So this represents the power which is going in and coming out of the magnetic field of L, and this represents the power consumed by the circuit. Power consumed by the circuit. I hope you have written down these equations. This represents the power consumed by the equation. Now, if I am taking that component alone outside, very interestingly, this is what we have taken. Power consumed. P, capital P is Vm Im by 2 cos phi. Vm Im by 2 I can write as Vm by root 2, Im by root 2 cos phi, or P is equal to Vi cos phi. This is the equation for power consumed in an RC, RL, in our case RL network or RL series circuit. Now and this particular term cos phi is called as the power factor of the circuit. Power factor of the circuit. Cos phi will be equal to R by Z. If you look at that, R by Z. When you see the power diagram, phasor diagram, the phasor diagram, which is because it is VR by V, VR by V, VR is IR, V is IZ. From where you get cos phi is R by Z. Now, and let us check whether this equation is correct. Now, V can be written as I into Z. Voltage V is equal to I into R plus JXL. We had already found out. So, I into Z into I. Cos phi I can write as R by Z. So, finally, I end up with I squared R. Or the power consumed is entirely by the resistance. P is equal to Vi cos phi is the same as I squared R, or whole of the power given to the circuit. The part which is consumed in the resistance part alone. I hope this is clear to you. Now, I want all of you to just think about what I have told you till now. I'll come back to the presentation again, but now I want you to, respond to whatever I have discussed. Come on. Now, what we have discussed today was in AC circuits, instead of having just a resistance alone, the AC circuit can have two more elements coming in. When you give a AC input to the circuit can have a resistance, or it can have an inductance and also capacitance. Now, in this particular class, what we dealt with was pure resistance was dealt with earlier. Today we dealt with pure inductance and then pure capacitance. If it is a purely resistive circuit, V is equal to Vm sin omega t, I is equal to Im sin omega t. When you draw the phases, both voltage and current will be in phase. And we saw that the power consumption was Vi, P is equal to Vi, just Vi if it's a purely resistive, nothing was there. Which will be the same as I squared R in that case. Okay. Then, when we passed on to purely inductive circuit, we saw that when you derive small v is equal to Vm sin omega t, small I is equal to Im sin omega t minus pi by 2. We use the equation V is equal to L di by dt and derive that. So, we saw that the current is lagging behind voltage by exactly 90 degrees if the circuit is purely inductive. And when you derive the instantaneous power, and then we went on, instantaneous power small p is equal to small v into small I. We just substitute small v as Vm sin omega t, small I as Im sin omega t minus pi by 2 and do the manipulations. And finally we get, and then we find out, and then we saw that there is a fluctuating element only in a purely inductive circuit. But then when you find out the average value, then the power becomes 0. Or we found our inference that was that if it's a purely inductive circuit, the power absorbed by the circuit is 0. If the power given to the circuit is taken up by the magnetic field or taken up by the inductance to build up its magnetic field, and then later on this magnetic field is when it collapses, when the current decreases, when it collapses, it gives it back to the source. Or it's called as a reactive power. It's not a true power. It's not being used. We'll come to that later also. Then we dealt with a purely capacitive circuit in which again we took small v is equal to Vm sin omega t and tried to arrive at the equation for I by using Q is equal to Cv equation. And then we saw that if small v is equal to Vm sin omega t, small I in a capacitive circuit will be I is equal to Im sin omega t plus pi by 2, or the current leads the capacitive voltage by 90 degrees. Again, we went on to find the power. We drew the power curve as well as we found out the instantaneous value of P, power P, small p is equal to small v into small I, where we substituted small v as Vm sin omega t, small I as Im sin omega t plus pi by 2. We did the arithmetic manipulations and finally ended up again with a single term, which is a fluctuating term or a symmetrical waveform, which means that over a whole cycle, the power consumed is again 0. And we came to the conclusion that in a purely capacitive circuit also, the power consumed is 0. Whatever power is or energy is supplied by the source is used up by the capacitance to build up an electrostatic field between the plates, and in the next instant or next cycle it's given back to the source. Again, it is a back and forth, the reactive power that is being transferred back and forth the source and the capacitance. Now, two terms that we came across in these two cases was, one is inductive reactance, XL is equal to omega L, omega is 2 pi f, where L is in henries, XL is equal to omega L is in ohms. And capacitive reactance XC is equal to 1 by C omega, where C is in farads, XC is again in ohms. And then we, after doing some problems, we passed on to a case where you are considering AC series circuits now. In AC series circuits, the first case that we took was RL series circuit. If it was a purely inductive circuit, L circuit, the current would have lagged behind voltage by 90 degrees. But when the resistance also came in, because you have a resistance and an inductance, the current will be lagging behind voltage by not 90 degrees, but by an angle phi, which is lesser than 90 degrees. How did we find out that? Here we took, when you draw the phasor diagram, because current is common for both resistance and inductance, we take current as a reference, I. And then VR will be in phase with I, VL will be leading because current is, should be lagging by 90 degrees. VL will be leading I by 90 degrees. So that I complete that triangle and I get that V are here, VL here, V is this. So that V will be leading I by an angle phi, which is less than 90 degrees. So then I found out P also, power P. And I draw the phasor, to draw the power curve also. P, instantaneous power P is equal to VI as in the previous cases, small v into small I. Here V is equal to Vm sin omega t, small I is equal to Im sin omega t minus phi. So again, arithmetic manipulations were done and we ended up with two terms. First term having cos phi is a constant value, Vm Im by 2 cos phi, and the other term is having a fluctuating value, which evidently, very clearly shows that in such a circuit where you are having an R and L in series, there is some amount of power consumed and some amount of power that is fluctuating. What is the amount of power consumed? Vm Im by 2 cos phi, which I can write as Vi cos phi, which I can also get it as Vi squared R, which means Vi cos phi is the same as I squared R, is the same as the power consumed by the resistance. Now here again we came across a new term, impedance. Impedance is nothing but capital V, that is the total voltage, resultant voltage V is equal to I into Z. As in the case of a resistive circuit, we'll have V is equal to I into R. In a purely inductive circuit, you will have V is equal to I into XL. In a purely capacitive circuit, you will have V is equal to I into XC. If it is a circuit having R and XL, R and L, you will have V is equal to I into Z, where Z is R plus JXL. So that we have found out. Now I will be stopping today and we'll be doing problems on this, before which I want all of you to work on something. I today discussed about RL series circuit. Now, when you come to the next class, make sure that you have written down all these things for RC network, series RC network, where you will see again V is equal to I into Z itself, but Z will be R minus JXL. R minus JXL. R minus JXC. So that much I would, because of the want of time, to save time, I want all of you to just look into this. Okay, I still remember one assignment that have been given to you for discussing and finding out an example. Only 3 batches had informed me regarding those Google Meets that they had done. I expect more. We'll find time for that presentation. ആ 3 ബാച്ചിലുള്ള 30 പേർക്കും ഞാൻ ആ അസൈൻമെന്റ് മാർക്ക് കൊടുക്കും. ബാക്കിയുള്ളവരുടെ കാര്യം അറിയത്തില്ല. Okay. So can you do at least that much for me? RC circuit നോക്കാൻ പറ്റുമോ?
Yes,
Rixin, have you studied RC? Rixin?
Yes, ma'am.
Have you studied RC circuit? Series circuit?
Yes,
So
ma'am.
just try to work that out and come. So, and one more thing I would like all of you to do is go through the calculator, the manual or something, and check how to do the calculations of J. Okay, conversion from polar to rectangular, rectangular to polar. That conversion you have to check in all of your calculators. Okay, so that's all for today. Thank you.